Welcome, everybody, to our November Science Positive Classes. Randall said, we are very pleased to have Dr. Kristine DeLong at Louisiana State University. Kristine is one of the original groups that are part of the South Central Climate Adaptation Center. So we've been working together for quite a while. In fact, a number of us just finished up a 3-day workshop last week. We were talking about some of the future projects that we were going to be doing. And Kristine's leading the charge with understanding changes along the Gulf Coast, including all of Texas, Louisiana. So that's going to be an important aspect as we deal with climate change over the next 50 to 100 years. But today, Kristine's going to talk to us about her work with corals and how we use corals to understand past climate change. And as I was looking at her CV on her website, I didn't realize that her Bachelor of Science degree is in mechanical engineering, and then she transitioned to study geological oceanography. So there's hope for all you engineers out there to move into some interesting things rather than just doing engineering. So Kristine, we're very pleased that you're with us. For those of you who are joining us for the first time, just to let you know, please go ahead and put your questions in the Q&A or the chat, and then I will moderate and answer. So to allow Kristine the full hour to talk to us about corals and climate change, Dr. Kristine DeLong. Thanks, Kristine.
All right. Thanks, John. So let me share my screen, and I have some slides here so we can see those. All right. Good. Well, thank you so much for having me back to Science by the Glass. So I've got my glass here, but there's just water in it. But today I'm going to talk about my coral work. And so this is something over the last 10 years I've shifted from working in the Pacific Ocean to working in the Intra-America Sea. And this lovely picture I have in my background, this is actually from Little Cayman Island, and we're actually looking at a fossilized coral reef. And this reef is 125,000 years old. So just to orient you to what I'm going to talk about, the Intra-America Sea is just the easy way of saying the Gulf of Mexico and the Caribbean as one group of water bodies. Sorry, stumbling there. But we want to study this particular region because there's a lot of people that live along the Intra-America Sea in North America and Central America, and also within the Caribbean. And this plus 120 million people are all vulnerable to climate change and natural hazards. So we're getting close to the end of hurricane season right now. So we're all kind of getting close to breathing a sigh of relief, but we still got a little more to go. But understanding what's happening in this region is really important. So some of the things we've noticed from looking at instrumental data, and that's what this figure is showing you in the red, is that there's different trends in ocean temperature all throughout the Intra-America Sea. So over here by the Lesser Antilles Islands and Barbados, we have some of the highest warming rates in this region. Whereas as we move towards the Yucatan and Cuba, those rates start to drop. And you'll even notice there's some blue color here along Florida and the Yucatan that are actually seeing some decreasing trends. But then as we get closer to the Texas and Louisiana coast, these trends are increasing again. So there's a lot of variability in what's really a relatively small body of water. And this body of water is also part of the Western Hemisphere warm pool, which seasonally becomes warmer and cooler. And the size of that warm pool and how deep the warm water is in that warm pool drives how strong hurricanes are. So we want to understand these changes in the warm pool through time. We want to understand the interannual variability that's related to El Niños. We also want to understand the decadal variability that's related to the Atlantic multi-decadal oscillation in this region, because all of these things dictate whether we're going to have strong hurricanes or not. So El Nino years, we tend to have fewer hurricanes, whereas La Nina years, we tend to have more. And we're moving into another La Nina phase right now. So that means everybody on the Gulf Coast has to be prepared for more hurricanes next year. So other things we've noticed from looking at instrumental records is we're also seeing this drying trend. So in the Caribbean and Central America, they're not getting as much precipitation as they used to. So there's lots of things to pay attention to in the Intra-America Sea. Now, as I mentioned, I'm a paleoclimatologist. So what I do is I look at the present climate, but also the past. So I pulled up here is just a graph you may have seen before that shows temperatures for the last 1,000 years. The very end of this record, I put here in blue, this is the instrumental record. So things we could observe with scientific instruments. But when we get back before 150 years ago, we don't have instrumental records. So we have to use paleoclimate records to understand what temperatures of the past were like. And this is where paleoclimatology comes in. And the premise we work on is that the past is the key to the present and the future. So I'm going to study past climates so I can understand what's going on right now, but also into the future. So how do we do this? So we're going to use natural archives because we don't have thermometers in the past. So we're going to look at things like tree rings and pollen records and ice cores and lake records and cave records. So all of these things happen in the natural environment. And as a tree grows or as ice accumulates, it's recording what's happening in the environment around it. So for an archive, we need to have two things. We need to have a way to tell time, and we need to have a way to record what's happened in the environment. So let's talk about a tree ring first, because those are relatively easy and most people know what I'm talking about with a tree ring. So if we know the age of the outermost ring of the tree, we can count these rings going back to figure out the year. So we have a way to establish time in the archive. And then by looking at how wide a band is or how thin, that tells us if we had more precipitation that year or less. So tree rings is one example of what we can use to reconstruct past climate. Ice cores are a key archive that we use quite a bit of to understand what's been happening on really long time scales. So let me explain how an ice core works. So here you can see an image of an ice core, and these ice cores have layers in them just like our tree rings did. So if we know what the year is on the top, we can count these layers going back in time. And now we have a way to establish a chronology. We can look at the chemistry of that ice and start to understand what's happening with temperature. But ice cores have something really neat that happens with them. So when the snow is first falling, it's nice and fluffy, but through time it becomes more and more compact and the snow becomes ice. And what's interesting is you still have these open passages so air can diffuse down into the ice. But eventually all these little air pockets get sealed off from the atmosphere. And what you get is these little time capsules of past atmospheric gases sealed into the ice. So this allows paleoclimatologists to go in, look at the chemistry of the ice to reconstruct temperature, and then we can go in and look at these little time capsules of atmospheric gas, measure how much carbon dioxide is in that air bubble, and now we have a direct measurement of carbon dioxide in the atmosphere in the past. So this particular graph I'm showing you, this is from Antarctica, so the Vostok ice core records. And here we see these variations in carbon dioxide and temperature. They're moving together through time. And what we're looking at is the ice ages. And as we move over here to the right, that's present. We're going to move to our present conditions. So that's here at, at 0. So we're going to look at some corals from this very end of the graph. We're also going to look at some corals that are 1,000 years old from the medieval climactic optimum. And I'm also going to show you some corals from the last interglacial. This is a really interesting period, 125,000 years ago, when the Earth was in its last warm period. So there's an ice age in between the present and this interval. And we're going to go back and look at this interval as well. So just to kind of give you an overview of what I've been doing with research in my lab at LSU for the past 12 years. So my long-term goal is to build this network of corals and other reconstructions to understand past climate change for the last 250 years. We'll go back to the last 10,000 years and then back to the last interglacial. And this is work I just got funded through the National Science Foundation. So this is my long-term view of everything that's been happening in the Intra-America Sea. So I have worked with tree pollen and tree archives, so the ancient forest in Alabama that I presented last year at Science on the Glass. I've also worked with cave records and pollen records and historical records, but today we're going to go to the ocean and look at the coral records. So I'm going to show you some new data that's just coming out from Flower Garden Banks. I'll show some data that I worked on from dry tortugas from the Florida Keys, and then we're going to take a trip to the Cayman Islands to look at some fossil corals, and then also to the Dominican Republic and Haiti to look at those last interglacial corals. So how do we do this coral research? So first thing is we scuba dive, and unlike a tree core where we use a small increment borer, we have to put on our scuba gear and take out some hydraulic drills to core into our corals, because corals are rock and they're quite hard rock, so we have to use specialized equipment. But what we're going to do is go in and take a core out of the center of this colony, and we'll bring that back to the boat and we'll analyze it. Now, other ways we can collect corals, particularly fossil corals, is this is a picture here from Haiti. So these are corals that were actually uplifted by the 2010 earthquake. These corals were underwater, but when the earthquake occurred, the crust of the earth flexed up and these corals were exposed. So my colleague Fred Taylor here from Texas, University of Texas, is taking a slice out of that coral, and I'm going to show you some pictures of it later. And then in the Caymans, we're going to look at those last interglacial corals, and here we're using a small handheld drill to core into this large coral boulder that was actually thrown up on the beach by a tsunami. Once we get our coral cores back on the boat, we're going to take them into the lab, and we're going to take, you'll see the cores here are round. So we're going to take that round core and we're going to cut it up like a slice of bread, so into slices, or we call them slabs. Once we get those slabs, we can take an X-ray of them. And here's an X-ray of one of those corals. And just like a tree ring, they have bands in them. So if we know the year that we collected that core, we can go in and count the years and figure out our chronology as we go back in time. So once we know our chronology, then we're going to use our micromill. And this is one of my former master's students on the micromill drilling a coral. So this is a lot like the setup in a dentist office. We actually use dental drill bits to go into that rock and extract very small amounts of the coral rock. And we're going to take that into the lab and do analysis on that. So the things we're looking for is different chemical properties of that coral. So the main proxy I use is strontium calcium. So corals are made of calcium carbonate. And calcium and strontium have the same number of electrons in their outer shell. So strontium will substitute for calcium in the calcium carbonate matrix. And that substitution is driven by the temperature. So if I look at the ratio of strontium to calcium, I can reconstruct what temperature was in the past ocean when that little bit of coral was being grown by the coral. So we also have to think about what's happening in seawater, and the strontium calcium ratio of seawater is a constant on long time scales, so we don't worry about that. So this allows me to reconstruct temperature. We can also look at oxygen isotopes. We call this delta 18O. We're looking at the ratio of oxygen 18 to oxygen 16. And again, that how much 18 is in the skeleton versus 16 is driven by temperature. So we can use this to understand past temperature changes. But here we also have to consider the delta 18O as seawater, which is related to salinity. And salinity is related to evaporation and precipitation. So by using delta 18O and doing a paired analysis, we can start to understand something about hydroclimate by looking at salinity changes that are related to precipitation and evaporation. So this is work that we're going to start doing here over the next year. So other elements we can look at inside the coral skeleton tell us other things about the environment. So one I'm going to talk about today is barium calcium. And this is related to upwelling and runoff processes that happen in the ocean. So cadmium and phosphorus also tell us about upwelling and running, but I'm not going to discuss those today. We also have other proxies we look at in my lab. So magnesium, calcium, lithium mag, and uranium calcium. These are also related to temperatures. We look at rare earth elements to tell us something about dust and wind processes. We also look at carbon isotopes that tell us about cloudiness and productivity. So there's lots of different chemistries we can look at in the corals that tell us something about the past. And the ones here in bold are all ones I've done in my lab, but I'm not going to show all of these today. We also have different ways of dating besides counting the bands because we want to double check our chronologies. So we use uranium thorium dating in our corals, which is a very precise way of dating. Then I put down here at the bottom radiocarbon dating. It can be done in corals because they have carbon, but it's actually not as precise as our uranium thorium method. So we prefer to use uranium thorium. So this is just a shot here of my lab where all the magic happens. So this is our instrumentation. It's a inductively coupled plasma optical emission spectrometer. Basically what it does is it creates a plasma that's as hot as the surface of the sun. We take those coral samples and dilute them into acid, and then that solution gets injected into that plasma. And all of those electrons all of those atoms get nice and excited. And when they come down from that excited state, they're going to emit photons. And the spectrometer part of the instrument measures how many photons are present. And every photon has a different wavelength. And those wavelengths tell us what element is present. So we count how many photons for each wavelength, and now we know how much strontium and how much calcium or how much barium is present in our sample. So, and here's just some pictures of students in my lab working. So they're either drilling corals or weighing out samples. So we weigh out for this ICP about 100 micrograms. So for those of you who don't know what 100 micrograms is, it's about 5 grains of sand. So that's what we're going to dilute in acid and send it into the plasma. And then I'm really excited. This is our new water isotope analyzer. We just got installed in the lab 2 weeks ago, where we're going to start measuring isotopes of seawater. And we're also going to put a rain gauge up on the roof at LSU. And we're going to start measuring the water isotopes in rain every time we get a rainstorm. So that's all new stuff that's going to start happening. So let's go out and look at our first coral site. We're actually going to go to the only coral reef that's in Texas waters. This is Flower Garden Banks. And we're going to go to the western part of Flower Garden Banks. And that's what's shown here in this map. Flower Garden Banks is out on the edge of the continental shelf, and it's a rising salt dome. So as the dome is coming up, it's getting shallow enough where corals can establish themselves on this reef crest here in red. And the coral that we're seeing, that we're going to sample, is over here at the yellow dot. So this is a really cool place to go out and scuba dive. You have to take a liveaboard boat to get out there. It's about a 5 to 8 hour boat ride to get there. Normally people go out and stay for 3 days or 5 days if you go out on the commercial boat. And NOAA also maintains Flower Garden Banks as one of the national marine sanctuaries, and they go out there regularly as well. And here's a picture of one of their divers coring a large coral head there in Flower Garden Banks. And what we get back in the lab is, again, our x-rays and our coral slabs, and we know the year the coral was cored, so we're going to count those years. Then the color lines are where we went in and microsampled that coral using our dental drill setup that we have in the lab, and we're going to analyze that. So let's go look at the results from our Flower Garden Banks coral. And this is work that I started back a few years ago, and I have a new PhD student, Kylie Palmer, who's also part of the South Central Climate Adaptation Science Center. So she's finishing up this record, It's going to go back to 1751. She's done the data on the ICP back to 1780. So we're just waiting to finish up that last 30 years. And she's going to have a really beautiful record of what's been happening in the northern Gulf of Mexico. So here we're looking at just back to, 2005 when this coral was collected, back to the 1930s. And what we see is the temperatures are pretty normal throughout this record. Ooh, sorry. But we see that we do, sorry, my PowerPoint's going crazy. We do see that there are some intervals here where we get some really cold winters that happened back in the 1930s and 40s. Now we can compare this to other records, and this is the dry tortugas record that I worked on from the Florida Keys. So the dry tortugas record is in blue and flower garden is in red, and dry tortugas is further south. So one of the things that you see by comparing these two records is that dry tortugas is warmer than flower garden banks. But you'll notice here in the summer times, they both get to be about the same temperature in the summer. And some years they're warmer and some years they're a little cooler. Mean-wise, there is a difference in means, but what's really different with flower gardens is it does get quite a bit cooler in the winter compared to dry tortugas. And then there's one particular interval here that's really interesting, and this is the 1930s into 40s. So both records have this cooling trend that occurs, but flower garden banks gets quite a bit cooler. And for those of you who think back to history, what's going on in this interval? This is the Dust Bowl that's happening in Texas and Oklahoma. So at this time, we're seeing this decreasing temperature trend in the Gulf of Mexico. And as you get colder temperatures, that means less evaporation. Less evaporation leads to less precipitation. So here we're seeing this direct correlation to surface temperatures in the ocean corresponding to droughts that are occurring in the Midwest. Oh, sorry. So now let's switch gears and look at a different chemistry that we've been working on in flower garden banks. And this is work that Mudeep has been doing. And here's a picture of him. He's from Sri Lanka. So he's actually sitting on a fossil coral reef in Sri Lanka. And Mudeep was such an awesome student. He came to LSU just as the coronavirus pandemic started. So he was able to get work done while being locked away into a small room because of the pandemic. And one of the things we wanted to look at was what's happening with barium calcium in corals. And this is a different proxy that tells us about upwelling and it tells us about river runoff. But flower gardens is in a location that's really interesting. So here we've got Mudeep's data. So we've got an interval here is from the 1930s, and then we've got a later interval from the 1970s to 2005. And one of the things that jumps out is we have a mean difference between these two intervals. If we just look at the seasonal cycles, we see that there's a difference in the seasonal cycles for these two intervals, but it's also different from strontium calcium, which is our temperature proxy. So they have a different shape. So we're really interested in trying to understand what's driving seasonality in barium calcium and why has this average changed over time. So thinking about barium calcium and what can change that in seawater, the big contributions to barium are river discharge and upwelling. So in the Gulf, so my black star here, that's flower garden banks. You can see where it's located. Oops, sorry. Here's the Mississippi River, which puts a lot of sediment into the Gulf of Mexico. But when we start to look at currents, the Mississippi River this outflow tends to hug the coast, and the currents along the coast in the wintertime are moving to the west, and then in the summer they reverse direction. So Mississippi River waters are really not getting out to flower garden banks. And again, if we look at the seasonality of when Mississippi River flow increases, it's in the springtime. And that increase in barium we saw in our corals actually happens in late summer. We also put the Atchafalaya River up here. That's another river that comes out right about here that also puts sediment into the Gulf of Mexico. So we don't think river discharge is making its way out to flower gardens. And if we look at salinity measurements, we don't really see any freshening trends that occur all the way out here. Again, if there was big salinity changes and a lot of sediment, we probably wouldn't have corals out there, because corals like clear water because they have zooxanthellae, they have algae under their skin, and that algae is photosynthesizing and providing them with food. So if the water is very muddy, you're not going to find corals. It's one of the reasons why we don't have corals over in Louisiana. It's because the Mississippi River is just way too muddy. So you need to get out into the Gulf of Mexico on top of this salt dome where the water is nice and clear for corals to occur. So now we got to start thinking about, well, how does barium behave in seawater to understand what's happening in our coral barium record? So here we're looking at a nutrient profile, or a profile of barium in the water, and it looks like a nutrient profile. So in the surface waters, there's very little barium, but as we go deeper in the water column, the barium increases. So oceanographers call this a nutrient-like behavior, because what happens is in the surface waters, there's lots of phytoplankton and algae, and they take up the nutrients and they use them very quickly. So all the nutrients go almost to zero. But then when all that plankton dies and sinks in the ocean, it gets recycled. So now those nutrients are released down into the deeper waters. And when we look at upwelling, this is when these deeper waters make their way back to the surface and adding nutrients to the surface. And upwelling occurs along the equator. It can happen along northern coastlines, like the Yucatan Peninsula has upwelling. But out at flower gardens, we don't see a lot of evidence of strong upwelling. There may be a little bit of springtime upwelling when the winds change directions. But again, it's not something we would expect to see a huge amount of upwelling. So this kind of leads us to thinking about anthropogenic activities that could be changing barium in seawater. So now thinking about seasonality in this nutrient profile. So if we look at our coral record and look at the bottom two images here, this is looking at chlorophyll, which tells us about phytoplankton in the Gulf of Mexico. So we've got an image here from the summer and one from the winter. So flower garden banks is out here. So what we see is in the summertime, there's less plankton than in the winter. So we actually get more plankton in the winter in the Gulf of Mexico. So more plankton means less nutrients in the surface water, which means less barium. So if we look at our graph up here and the plankton or the chlorophyll A, I've actually reversed that so that you see that when there's more plankton, so the chlorophyll numbers decrease, and this corresponds to the decrease in barium. So what we're seeing with the seasonality with barium in our corals is the seasonality that happens with productivity in the Gulf of Mexico. So as the Gulf becomes more productive, there's the nutrients get drawn down, the barium's getting drawn down at the same time. And then when that productivity decreases in the summertime, the barium values increase as the plankton numbers decrease. So this is explaining why we see the seasonality in our coral record. But now let's go back to that mean shift and think about why we're seeing a mean shift in the corals. And this is going to go back to what we use barium for, particularly in the Gulf of Mexico, and that is drilling muds. So barite, which is barium sulfate, is used heavily by the oil industry. Matter of fact, 90% of all the barite produced in the US is being used for oil drilling. And it's thought that the barite, after it's used for drilling, it just sits in the sediments on the seafloor and it doesn't dissolve. So it's supposed to stay out here on the seafloor. And these are just two images showing you oil platforms. So this bottom image, that's actually one from Flower Garden Banks. So the oil platform, when we were out there diving, this platform has now been decommissioned and removed. And this map up top just shows you all of the oil platforms out in the Gulf of Mexico from US and also Mexican oil producers. So we have lots of oil production in the Gulf of Mexico, which means lots of oil drilling and lots of barite going out to the Gulf of Mexico. So going in and looking at our barium data, and what I've done here is we've just taken the annual average to take that seasonality out of the coral records. So for our earlier interval, we're seeing this mean value of barium in our corals. And this amount that we're seeing, so the lower blue line is about 30 nanomolars per kilogram. That's a typical open ocean amount of barium. So what we see in the Gulf of Mexico is slightly elevated levels in the Gulf, but we have the Mississippi River. But what's really noticeable is this huge increase that happens in the 1980s. And this corresponds to oil production in the Gulf of Mexico really taking off. Going up to about 1980, and then oil prices drop and oil production offshore also decreases. And we see the coral records showing that decrease almost in step with what's happening with oil production in the Gulf of Mexico. So we're thinking that this mean shift that we're seeing and these changes in the annual variability of the coral barium, it's corresponding to what's happening with oil production offshore. So this is a really interesting result, and Medivh was able to publish these results just about 2 months ago now. So this is hot off the presses. So let's switch gears and go back in our time machine a little further into the past to a period called the medieval climactic optimum, which happened about AD 950 to 1250. And this particular period you may have heard about. This is when it's thought that the Vikings went in and established themselves in Greenland. So there's less sea ice during this time. So Europeans are moving around. And it's a time period where in Europe, you start to have culture taking off because the winters are less severe. The glaciers are all receding. So they're getting this really nice time period at this interval. So, and we know a lot about what's happening in this interval in Europe, but we don't know a whole lot about it when we get into the IntraAmerica Seas. So just coming back, looking at our ice core records. So we just looked at the little ice age interval, or actually the 20th century. We'll be going back to the little ice age with our coral records in the Gulf of Mexico soon. But now we're going to come look at this medieval warm period. And see what's happening in the IntraAmerica Seas during that interval. So one of the things we see globally is that temperatures are 1 to 3 degrees Fahrenheit warmer. Little ice age is about 1 to 3 degrees Fahrenheit colder. So here we're going to look at some corals from Little Cayman Islands. And I was able to go out there in 2016 and 18 and collect a lot of corals. We were supposed to go out in 2020, but the pandemic happened, so we weren't allowed to travel out there. We didn't get to go there this past summer either, so hopefully next year we'll be able to get out there. But one of the things we're doing is coring live corals in Little Cayman, but also picking up a lot of these fossil corals that are all around the island. And these corals are all been washed ashore by hurricanes. So one of the things we're doing is picking up some of these larger corals and dating them. And we see this wide range of dates. We get a lot of them that are 5,000 years old. And we have quite a few that are about 1,300 years old. So we're going to look at this 1,300-year-old coral first. And this is work that an undergrad, Kendall Brome, did with me at LSU as part of her undergraduate research project. So what we're finding in this coral that's growing just before that medieval climactic optimum is that Little Cayman has temperatures that are very similar to today. We also looked at the barium calcium in this coral because the north side of the island can have upwelling due to the direction of the trade winds. So we do see intervals where we get these really nice peaks in barium that's telling us that we have stronger trade winds during this interval. So this is work that I'm going to continue to do here in the next couple of years in the Caymans. We brought back 40 different corals, and we'll start processing those and doing work on those here in the near future. And we'll be able to start looking at how temperatures changed in the Caribbean for the last 10,000 years. So as I mentioned, we're just getting all of this getting it all going again since the pandemic started. So now let's go back a little further in time in the Ice Age, and I'm going to pull this plot back up, and we're going to come in and look at, this last interglacial interval right here, so 125,000 years ago. So what the Earth is like during this time is really interesting, and that's because it's a possible analog for future climate change. The other thing that happens during this time is we have higher sea levels than today. So they're 6 to 9 meters. So that's 18 to about 36 feet higher than today. So a lot higher. So for living here in Baton Rouge, we're about 30 feet above sea level. So at this time, Baton Rouge would have been a coastal city. We would have been beachfront property. So, and again, this is natural climate change. This has nothing to do with humans. So more ice is melted in Greenland and Antarctica during this interval. We also have stronger orbital forcing during this time. So this leads to a really strong seasonal contrast in the Northern Hemisphere. And again, these are particular conditions we're interested in for understanding future climate change. For paleoclimate records going back to this interval 125,000 years ago, most of them do not have seasonal resolution. So they generally tend to be marine sediment core records that maybe are 100-year resolution. So being able to look at seasonality for this interval is quite rare. So I'll show you some pictures of the corals we're going to look at. So this is the coral that's from the north coast of Hispaniola. It's dated to 128,000 years ago. So it's right at the beginning of that last interglacial period. And this core this coral piece has 75 years in it. So we've got a nice long record of what's happening in Hispaniola at this time. We're also going to compare this to a modern coral from Haiti. So this is one of those uplifted corals. And here's the x-rays from these cross sections. So we have 3 of these in our lab that we've been looking at. And this was work that my former PhD student, Gil, worked on. So what we see in Hispaniola in this 75-year record is these really strong interdecadal and decadal variability that's happening during the last interglacial period. But let's compare that to what we're seeing with the modern coral in Hispaniola. And this is where these differences really pop out. So looking at the modern coral, they have about the same average temperature in both of these, but the variability is quite a bit different. So the last interglacial has stronger variability. It also has stronger interannual variability. So that's that El Nino type of climate change or climate variability. And the decadal variability is also quite a bit stronger during the last interglacial. So this is telling us that in this warmer interval in the past, things were quite a bit stronger with the interannual and decadal variability, even though the temperatures were exactly the same. So other things that we've been looking at is taking this data and comparing it to climate models. And this is work I've been doing with one of our colleagues at the South Central Climate Adaptation Science Center. And here we're looking at different climate models for 125,000 years ago, the 20th century. This is a control run, and then the HAD ISST and the ERSST, these are both instrumental temperature records. So by looking at these climate simulations for these different intervals and comparing them to our coral records, we can start to tease apart how the climate models and the coral records are different. So one of the things that's been noticed by researchers is that the models have a cold bias in them. So the models don't quite get these warmest temperatures. So that's an issue that climate modelers are trying to address. So if we look at our coral reconstruction, so here I'm just showing that seasonality by January, February to December. So if we look at the model simulations versus the temperature. So the temperature records are in blue and green. The model simulations are purple and red, and you can see that cold bias that exists between the instrumental records and the climate models. But what's interesting is we also notice that the climate models also have the seasonality for the last interglacial of about 3.7 degrees. If we plot up the coral, it has the same seasonality as the model, but the corals are quite a bit warmer. So the corals seem to not have this cold bias in them that is noticed for the 20th century interval. So this is really interesting because it gives us another way to check the climate models in the past to see are there cold biases or not. And understanding these biases are really important, particularly when you think about things like hurricanes, because hurricanes tend to form when you get ocean temperatures above 26.5 degrees Celsius. So if we went by the climate model that had this bias, you would think that, oh, this isn't getting cold enough or warm enough for hurricanes. Versus if you look at the paleoclimate reconstruction, it says, oh no, we are definitely over the threshold for hurricanes. So resolving these biases are very important. So I'll wrap things up here from what I've shown you from looking at modern corals and fossil corals, and we're using this information to help understand our climate model data. We're building this big network of what's happening in the IntraAmerica Seas, so we can understand other processes that are happening within the region. And we're really excited about our new barium proxy that we've been using here in the Gulf of Mexico. So stay tuned, there's a lot more to come. We're gonna be really busy here over the next couple of years, getting this project off the ground. So thank you for letting me share these results so far.
Kristine.